Well, good afternoon, everybody. If we're a bit confused by the title, do not blame me, but thank Kenny Crackhorn over there. I get a call from Kenny Crackhorn about a month or two ago, and he's like, "Hey, we're having the conference. Can you, come and talk?" And I'm like, "Sure. What do you want me to talk about?" "Oh, I don't know. What have you been up to?" And so I tell him what I was up to, and he's like, "Okay." And next day I get a thing, "Yeah, we decided you're going to talk about the yield triangle." And I'm like, "Well, like at that, that disease thing, just talk about it in terms of yield." And I'm like, Kenny Crackhorn be smoking some of that Kenny Crackhorn or left-handed hemp cigarettes or something? I don't know. But actually, when I went away and I started to think about it more, it's actually not a bad way to think about yield, because when we depict things into shapes like the yield triangle, what we're talking about is just trying to understand the relationships. And so that's what I've tried to do today. And what I'd like to do is acknowledge my co-authors here who contributed greatly to this. Dr. John Kirkgard with CIRO out of Australia, Jerry Hatfield, USDA out of Ames, Iowa, James Hunt, also from Australia, Malcolm Morrison, a physiologist with us out of Ottawa, and Rob Graff, whom I'm sure most of you know is a plant breeder here at Lethbridge. So this is Exhibit A. This is the first kind of understanding that I visualize around how yield has evolved from, say, the turn of the 19th century, 20th century to what we're seeing today. And this isn't sort of an interdependent sort of relationship. This is more of a cascading effect of building blocks where you need those productive soils in order to move up into more methods. And this is sort of the context around how I'll be talking today, leading right up to the philosophy around integrating the G, which are the genetics, with the M, the management, and how you try and, as much as possible, couple those together so you can overcome what you don't have control of, and that's the environment. So if we think back to Canada's history around crop production and research, actually, they coincided at the same time, which was pretty cool, because we had this dedicated policy within government to get the West populated and settled, and that happened through farming, through turning over the sod, but it also coincided with the strategy of sending out Dominion of Canada scientists at the same time in order to establish the methods that would retain those settlements and get us our railroad basically across Canada. And so it's one of the few examples of where we've had the scientists landing at the same time as the farmer globally. What's also really cool is at the same time, these are very bright scientists. We talk about all these fancy philosophies today. Well, they had those philosophies back then. It was just a little bit harder to achieve the uptake. And so they set about initiating some of these crop rotation studies that if you've ever toured Lethbridge, the research center, you would have seen some of these that are still in production today, and they're still yielding valuable information. The downside to what was happening when we were breaking the sod is that in some areas we didn't have that first building block, for example, of good soil. Where we did have good soil, we sort of degraded it by methods that were prone to soil erosion and that sort of thing. And that's where agronomists and those scientists had to come in to come up with solutions in order to sustain and reverse some of those detrimental impacts on agriculture. And if you're really interested, I'd highly recommend this book edited by Wayne Lindwall and Bernie Sontag. And there's a really good chapter about how sort of this whole no-till evolution really laid the groundwork and was really the only thing that stood between us maintaining that kind of scenario versus moving into things like high crop diversity and allowing us to achieve and get to those upper ends of yield and the full coupling of G by E by M. And so agronomy, sometimes, you get some smart-ass colleagues, "Oh, agronomy, it's like glorified gardening or whatever," and I'm a little sensitive to that, and apparently so is my colleague from Australia. It's really come a long way, and you guys that are farmers know it's not like it used to be. It's highly complex, and as John says here, it is rocket science, just because of so much change happening so rapidly in terms of what the challenges are, what your opportunities are, and how you're integrating all these different disciplines and information from these disciplines into a cohesive, thoughtful system on your farm. That's even before we start talking about the digital age around what's happening, which has really become space age. And of course, we can't forget the agronomic methods and practices that occurred within the Martian movie, of course. So there you go, rocket science. So what's coming along at the same time is we're having these emerging issues. Not a big surprise, wouldn't surprise anybody here to talk about those stresses. This is some data that Malcolm Morrison put together that puts a new context on where we're at with some of these things. 1.2% as far as how our food production currently is increasing, and that's going to leave us about 40% in the hole. And one thing you'll hear about is that there's a very strong relationship between food security and global stability. As we become food insecure, that's when we become much more unstable in certain areas where they have that issue, and I'll talk a little bit more about that later. The one thing that's a bit troubling is, yes, we're going to see rises in temperature. Doesn't matter how it's come about, but that's the fact. It's this whole thing of CO2 and how much CO2 can we put up with within our farming systems and our environments before we can't manage our way around it anymore. And that leads us back to this thing and the understanding around yield gap and what actually contributes to yield. And the way I think about yield is basically starting off in sort of this linear fashion of that V, the variety, and how we're trying to couple that with the A, the agronomy, and how we're trying to manage those two around what's really a random effect being environment, and that being Mother Nature. And we know what she can be like, so we have to just try and temper that as much as we can. And the more I guess, academic or more modern take on that is when you actually take this G by E by M approach, which is more of a globally accepted term. You'll start hearing more and more about that in Canada as well, where we're trying to get that synergistic effect where it's not really additive, it's more multiplicative in terms of those relationships between the G, the E, and the M. And so this is where agronomy comes in. That potential of that genotype, that variety you just purchased that's fresh out of a breeding program, whether it be private or public, what's it capable of yielding, and what are you achieving on your farm? So there's that gap. And what does that gap look like? And how can we minimize it? And that's where, from an agronomic and a scientist point of view, is where we try to fit in to try and minimize that as much as possible. Nice classic example of how that works would be the corn model in the US. What people sometimes don't realize is we had hybrids in corn going back to the 1930s, but we did not exploit any additional yield out of that until we figured out how to couple that new genetics with management. The E, by the way, will always be changing. So if you look at how things started to scale up, well, first, some of the E was related to nitrogen, nutrient management. Then we had nitrogen fertilizer. You see a bump in yield. Then we had weed issues. We come up with herbicide tolerance. We overcome that. Now the environment's insect related. We come up with BT genes and we overcome that. So it's just that ever-changing dynamic of random variables that hit you on your farm that you have to be able to manage your way around. What is the gap on your farm? I don't know. Globally, though, we know it's around 48% with wheat, which is terribly low when you think about the investment in breeding and genetics and how we're actually capturing that investment back on the farm based on what we're paying for seed input costs and what we're realizing from that. In Australia, Jerry Hatfield, as part of our work with the Wheat Initiative, has done some yield gap work, and basically these are just observations from FAO stat data that he put together, and it's called a quartile sensitive analysis, but basically all he's done is he's drawn a line through the really high hits, saying that that's probably years where we didn't have too much limiting yield, and all those observations below that would represent realized things that just didn't and make up, and that's where your gap comes from and looks like on the right-hand graph there. So it's bouncing all over almost in a shotgun pattern, not much stable or consistency around it. We're a little bit more stable in Canada, where we see us thankfully having higher yields overall, but also kind of more of a tightened line around, say, 400 kilograms per hectare in terms of a gap. And you can do the math on that. And I'm not, the only part about this is how much of that line represents the genetic potential versus just a guess. And I would suggest the genetic potential is probably even higher, which means the gap is even higher. And so compared to Australia, that's what we look like in terms of if you took that actual yield and you divided it by the attainable yield. You'd want to be on that y-axis as close to 1 as possible. In some years, we're hitting that very closely in Canada. Other years, we're bottoming out at 50%. So still quite a bit of work to do. And so what I'll do is I'll lead into some just real quick snapshot examples of the M component and some work that we did on diversity, but also some interesting work by Angus et al. And his colleagues around taking as many studies as possible to understand how can you maximize your wheat crop, for example, because it's in rotation and it's going to be influenced by that preceding crop, obviously. So they looked at studies that had all these different preceding crops, from oats to oil seeds to pulses, and how that affected responses of wheat that followed it. And a little bit of a surprise to me, actually. Oats, not a surprise, it was the lowest for a number of different reasons, but following that, oil seeds, and they're saying that pulses were giving them the best response in wheat when wheat followed pulses versus canola. I would actually argue with that or suggest that our experiences in Canada are a little bit different. And the results and rationale behind that is this study here that we ran for 7 years. Using our typical agronomy equipment, as you see in that picture there, a range of crop phases, but basically the whole point of this was looking at responses of cereals when cropped with, or when exposed to differing levels of diversity. And a few surprises came out. The one, I guess, nice surprise is that as far as yield of that cereal phase goes, is that it does respond to diversity. So diversifying is a good thing. The inclusion of peas, as you see there, is a good thing. But as you also note, intermediate between peas, 2-year rotations of cereals and peas is the canola and the cereals, which is not significantly different actually than the high diverse. And that's not really a big surprise. You've probably seen other research on this. If you look at the yield there and the effect for it, you'll see it's 0.921, which is non-significant, obviously. And basically what that's telling us is that canola doesn't respond to diversity, at least in the short term. And that's what we're seeing. That's why we're seeing farms getting away with super tight canola rotations, and it's making them more money in the short term. It's because you can run a 2-year rotation with canola and wheat, and the canola is gonna pay you some pretty good money in the short term before the system starts to break down from things like diseases and so on. But interesting. What you don't see and what you never see when you go and visit plots in our farm or wherever our other research farms is where the peas are making the biggest difference, and they're making the biggest difference below ground. Mike had some information on cover crops, same thing, that below ground response, hard to pick up and show at a field day, but this is what you see in 3 of the 4 rotations. They included a field pea phase in terms of looking at microbial biomass C as a proxy for soil health. So an extremely important aspect for below ground stuff, which you don't normally see or take into account. The other nice thing about this one in the green there was that in medium to high production environments, diversity pays and does beat triticale, and in this case canola. So the 2-year canola wasn't making as much money as a 3-year that included the peas, at least in this scenario. So how do the breeders exploit the G, and what does that yield triangle look for them? And they're under some pretty looming and concerning prospects around where their breeding progress needs to take them versus with wheat where we're at right around 0.7 to 1% gains per year. It's got to change a lot differently in the coming years, and how are they going to do that? So how does a breeder manipulate that? Well, he or she incorporates traits into that plant that result in changes to the yield components, whether it's seeds per spike, spikes per plant, leading to weight per seed, whatever. It's traits that'll at some point lead to changes in that'll ultimately lead to increases in yield. And so that's what they're targeting, and that's what their yield triangle looks like. And rather than some hierarchical thing, for them, it's about that area. They're locked into that area because of in this case, yield, protein, and maturity. So for example, if you wanted earlier maturity and you pulled in that direction, you would have to squash down the yield. So you're going to suffer yield at a cost to having whatever maturity you're after, early in this case. Protein, same thing. If you want to pull it that way, you're going to have to pull down the yield. And so it's the area that they're fixed into, and that's the one thing they're trying to break out of, and it applies to the yield components as well. And so this is the difficulty that breeders face, is how can they incorporate the latest technologies to try and push that out, that area. As far as integration, and I thought this would be kind of, given the year we had, I thought this would be a pretty pertinent example of what's been going on in Australia in terms of some really good studies where they integrate the G with the management to overcome the environment. In this case for them, it's water stress. And so this is some work that John Kirkard had done. And I like the way he's visualized that. You've got all this management influence at your disposal prior to planting that range from all sorts of things related to soil, disease management, nitrogen, you name it, weed control. And then once you move into in-crop management, now you're dealing with sort of that 50-50 balance of the management influencing yield as well as whatever genetics you've incorporated to manage that yield as well. And these were kind of the themes they had worked on and touched on as part of trying to boost what are pretty low yields for wheat in Australia. And this is sort of what it looks like. The upper part there is sort of the conventional old-timer type systems where continuous wheat, weed control not the greatest. They even do some old cowboy things like burning and cultivating or planting late with their cereals. And not necessarily using the most latest, greatest genetics. And they've evolved greatly and have adopted our canola and integrated that. They've got a better handle on weed control and some of the resistance issues they have with herbicides. They've adopted no-till, and they're moving in this direction of altering their seeding times in which they plant their cereals. And the one thing they did that was really cool was they worked with plant breeders, the agronomists, to develop a strain of wheat that would help them overcome the water stress that they have. And basically, it was pretty much tripling the length of the coleoptile. So these genotypes that they incorporate have if you can see it, I don't know how well that's showing up there, but basically, they've gone from an inch and a half coleoptile length to 3-4 inches in depth. And that's allowing that root mass to chase moisture and more efficiently utilize it. And then what they did is they took that, and this is where Farming Smarter, I think, fits in nicely in research like this. They then took and scaled that research up, put it into on-farm demonstrations, on-farm research, and the result was they were able to confirm and even fine-tune some of the practices that we're doing in relation to the different varieties and that sort of thing, and basically able to show returns on investment and also the real fine line around the economics of all of these different systems. The one thing we're looking at in relation to one example of some of the work we do as far as G by E by M is ultra-early seeding systems. And if you look at some of these climate change scenarios, a lot of times Canada actually fares quite well. So I wouldn't be so worried or concerned about pushing back on climate change scenarios because actually some of them support a net positive for Canada. This one's a bit 50-50, but in some ways I think it still is a net positive for Canada. The left-handed scenarios there from top to bottom are 2020 at the top left down to 2080 and how that might change. But keep in mind, first off, green is good, but secondly, that's based on today's practices, today's genetic potential, today's attainable yield. And so what it tells me is there's still hope and promise on the Canadian aspect at least. Some others won't fare as well. I know Malcolm was bugging our Australian co-authors that Australia is going to dry up and blow away. Could be. They told us we were going to thaw out and melt away, so we'll see. But I think in the context of with some adaptation and nothing even too extreme, I think it is a net positive for Canada. One of the things I still, and some of you know me as a winter wheat agronomist, one of the things I think we're going to be doing more of in decades to come are growing crops with a winter growth habit instead of a spring growth habit. And it probably starts with the best example of winter wheat and balancing and stabilizing that yield and even increasing it. I don't see why we can't have as much winter wheat out there as we do durum, for example, especially with the fusarium issues. The other thing that we're doing is we're working with breeders looking at cold tolerant spring wheat lines and basically reassessing when we should be planting wheat. The idea is we sort of get out there and plant some other things like canola, perhaps maybe peas earlier, and we kind of wait and we still have in our mind, you know, as long as I'm in by May 10th, I'm good. Even some of the recommendations about when to go in as far as soil temperature, you know, they say roughly 10 degrees soil temperatures in the top 5 centimeters. I don't know about that. I think the other problem we have with planting dates in general is we're still talking about calendar dates, which are totally meaningless and are just a snapshot in space and time that you really can't extrapolate out to. Better yet would be using soil temperature as a trigger point. And so for us in this study, 0 degrees C in the top 5 centimeters is our trigger point to get out and start planting, which seems a little extreme. It's not going to be able to be done everywhere, but particularly in the south here, it's easily done. And in this case, as early as February 16th with actually pretty good results. And basically what we're learning with some of this in the preliminary results is that if you waited until the recommended on the far right of that x-axis of 10 degrees C, you'd be suffering quite a yield drag compared to going in at, say, 2 degrees, which is a bit of a, the result was more surprising than I thought we would achieve. And then that's even before we start looking at really being able to exploit a cold tolerant gene, because so far what we're seeing in the germplasm and where we're doing our work is that even just taking a regular bread wheat variety like Stettler works just as well. And so is there opportunity to incorporate genes around cold tolerance to really allow that? The other thing that we're seeing, and we've published on previously, is that a lot of that might be mitigated and masked over by the fact that we're recommending and encouraging the use of dual fungicide insecticide seed treatments, because we know irrespective of what you have for insecticide pressure, disease pressure, those types of compounds will change metabolic pathways within the plant and make it more tolerant to abiotic stress. And that's the key, and where I at least see the promise of going with seed treatments. It's around that abiotic stress, not even so much the biotic factors. The funny thing was, as we initiated this study, our counterparts in Australia, without us knowing, without them knowing, they initiated one as well. And their part about early sowing systems is all about the fact that, unlike here, their yield is actually flattened out for wheat. And it's all around moisture and high temperatures, and not just a cyclical thing. It looks like the tap's kind of been turned down for the long term. And so Dr. James Hunt, they started looking at, well, how can we break the synchrony of when we normally plant to try and, with what little water there is there, to try and maximize it. And so they started looking at all sorts of different things. Ironically, winter wheat. How can they integrate winter wheat and the advantages? And if you look at the challenges of winter wheat, they're exactly what we were facing with winter wheat a decade ago. Poor investment, not as many varieties, and especially compared to the number of varieties of spring cultivars that have come out. And basically what these guys are doing is shifting and trying to shift when they plant so that they can get that flowering over and done with before that real heat stress hits, again, that abiotic stress of that heat in this case. And they're having some pretty good success with it, I would say, based on what John presented in October at a meeting we were all at. So looking ahead, obviously there's going to be new challenges, but if you had to pick one new tool in the face of all these things that are occurring, what would it be? We could spend the next 3 hours talking about where to exploit all this different stuff and how it fits. But I think if I found one example, and the only reason I'm thinking of this one is because I was kind of volunteered to get involved in an Ag Canada workshop around phenomics But is that the next step? Is that the next thing that's going to change, at least on the G side, to help us overcome some of these issues on the environmental side? And basically, what is all this about? Well, as far as definitions go, it's basically two very simple things. The phenotype is simply the variety you plant in your field is the phenotype. The genotype from the lab doesn't necessarily look the same as the variety expressed on your farm for a number of different reasons, which I'm sure you understand. The phenotyping aspect part is just the measuring of those changes that occur between the genotype and that phenotype. And it's very, the advantage of what potentially could happen, for example, any of the yield data that Ken and his crew presented today from the combine, that's a phenotyper. Why? Because it's measuring yield. Yield we're not using to talk about X versus Y. That yield is actually a prediction of what that phenotype's going to perform like in the future. Can we find a better way to do that way before that crop is actually even flowered or even ripened or is ready to harvest? High throughput phenotyping is kind of the key to that. And basically it's all about speeding the breeding because you're dealing with this monumental amount of data. How do we synthesize that so that we can improve selection precision? That's what it's all about. And there's now starting to be some headway, and some pretty serious money has been set aside with Ag Canada about going forward with some sort of a transformative project around it. And what lends itself to a multidisciplinary, transdisciplinary science is something like phenomics, because it gets so many different components and disciplines together. And the key, I think, the only holdup in my mind will be some of these disciplines don't play nice with one another. And I think that's going to be sort of the paradigm shift that needs to happen as we go forward. And what Malcolm's saying here is phenomics is a really good example, therefore, of combining genetics with the management to go overcome that, that environment. The other thing that I think is really important moving forward, and you even see it with the commissions and so on, is the whole idea around partnerships. And how is partnerships going to evolve to really drive science? Because if you want these changes, if you want progress on your farm, you need science, and science needs to partner up probably more efficiently and more effectively than ever. One of the things I'm involved in is this wheat initiative, I think that was alluded to earlier. This is a pretty cool thing that actually spawned from a food security issue that happened a few years ago. So much so that the G20 ag ministers got together and said, you know, we got some issues globally with wheat production. We need to get our heads together, and thereby was born the wheat initiative. And I was actually volunteered as well to be part of that, sitting on the research committee. What's important in something like this schematic isn't the three bodies running it. It's those little dots at the bottom there that are actually the expert working groups. So those are the scientists that are getting together and working and trying to come up with a way to better work at a global level to actually make a difference on your farm at the farm level. And we need to even rope in, I think, Farming Smarter, because so far, all we've done with Farming Smarter is talk them into buying us lunch last October. So we're going to get Ken and his crew, I think, involved in working on this expert working group as well. And I would say it's a great sacrifice, and I think you should all be sympathizing for me. The locations of these meetings are horrible. Instead of coffee, they serve you Bordeaux in the middle of the afternoon. And as you can see, the stress is written all over Dr. Curtis Pozniak's face there of having to attend these meetings just in front of the Eiffel Tower. Our colleagues like to meet in Europe. That's probably the only downside of that interaction. And again, this is sort of where we're at, is developing this agronomy expert working group. Even globally, if this initiative were to fall apart, I think this is something that's desperately needed in Canada, is bringing an expert working group together of agronomists and all those disciplines, as well as stakeholders and groups like Farming Smarter, that will actually bring it together, because we're a bit fragmented, I think, and I think there's still opportunity there. And so I'm going to end with my last exhibit C here of a yield triangle, and this, I think, is really what really hits home, or what I would drive home, is if you can really maximize genetics and the management, what you do is you start to expand the triangle, and you expand that sweet spot in the middle where your optimum yield is coming from. So with that, I thank you for your attention.
All right, this is your opportunity to ask him all about the Bordeaux in France at coffee breaks. No, actually, if you want to find out more about the yield triangle and that he talked about, the floor is open for any questions, if anyone has a question. So does this really take a kind of a holistic approach? Because if you spend too much time, even in the research world, on one element of the triangle without the others, does it throw things out of balance? Do you really have to be kind of working on all aspects and seeing how they relate together in order to try and get that triangle expanded?
Yeah, I think unfortunately we've got lots of examples in the past where we went to a magic bullet mentality. On the breeding side, a good example down south here was wheat stem sawfly management. Everybody was told by breeders, seed companies, whatever, that all you got to do is plant that solid stem variety. What was lacking is the understanding that that variety interacts greatly with environment, and sometimes it's as hollow as a hollow stem. And so what's required and what was necessary there was to build a system that coupled that. On the agronomy side, I think where we failed is we oversold the benefits of herbicide tolerance to the point now where we have weed resistance issues. We're no longer looking over the ocean at Australia's problem. We got a pretty good one ourselves now. And the solutions even to date, I think, are woefully lacking compared to the creativity that's going to be needed to overcome that.
Any other burning inquiries? Well, we thank you for the good work. Brian, just don't run away. I have a thank you card for you here. Thank you for the good work that you and your teams are doing. And I think it's very encouraging to see that trend to working together, that people aren't in their silos, that everyone is starting to cooperate and learn from each other. And that will help for the overall improvement in our production. So thank you very much for sharing your work with us here today.
Thanks, man.